Human beings eventually learned to manufacture winter, reshaping food, medicine, industry, and daily life. For most of history, useful ice arrived only when weather, geography, and season allowed it. Communities harvested natural ice from lakes, ponds, and rivers before machines could produce it. Insulated ice houses delayed melting, allowing winter cold to survive deep into the warmer season. Insulation cannot generate cooling. It merely slows heat flowing toward a colder object. In 1806, Frederick Tudor began building a business around shipping natural ice to warmer markets. Tudor initially lost money because customers had not yet learned to value imported cold. The demand expanded when businesses discovered that ice could preserve food, cool drinks, and relieve patients.
Natural ice evolved from a luxury into an urban supply system serving homes and commerce. An icebox cooled food passively as air circulated around a slowly melting block. Iceboxes required constant deliveries, cleaning, and drainage because their cooling source steadily disappeared.
Engineers began asking whether machinery could remove heat without waiting for winter. Temperature reflects microscopic motion, so cooling means reducing energy within a material or space. Evaporation cools a liquid because its most energetic molecules escape and carry heat away.
Human perspiration relies on evaporation to transfer body heat into the surrounding air.
Long before mechanical refrigerators, evaporative methods cooled water in dry climates without producing ice. Reducing pressure allows liquids to boil at lower temperatures and absorb heat more aggressively. In 1755, William Cullen demonstrated artificial cooling by evaporating fluid under reduced pressure. Cullen proved a physical principle, but his apparatus could not provide continuous practical refrigeration. Practical cooling required a reusable fluid, circulating continuously through changing pressure and temperature. During 1805, Oliver Evans described a closed vapor compression system before anyone successfully built one. Jacob Perkins constructed and patented an early working vapor compression refrigerator in 1834. The machine reused one working fluid instead of consuming a fresh supply during every cooling cycle. Inside the evaporator, low-pressure refrigerant boils and absorbs heat from the space being cooled. Compression raises vapor pressure and temperature, so the captured heat can be rejected elsewhere. The condenser releases absorbed heat to the environment and turns high-pressure vapor back into liquid. An expansion device lowers pressure, preparing the refrigerant to absorb heat during another evaporation. A refrigerator does not create cold. It repeatedly pumps heat from inside to outside. Every refrigerator warms its surroundings slightly because it releases both removed heat and operating energy. Once the cycle worked, engineers had to make it reliable, economical, and powerful enough for commerce. James Harrison developed commercial refrigeration machines that produced ice and cooled industrial processes during the 1850s. Brewers adopted refrigeration because stable temperatures improved fermentation, storage, and year-round production. Physician John Gorey pursued artificial ice to cool rooms and relieve patients suffering in tropical heat. Gorey's work connected mechanical refrigeration with indoor climate control, rather than food preservation alone. Ferdinand Carré's absorption machine used heat and chemical affinity instead of a large mechanical compressor. Absorption systems could create cooling wherever heat was available, even without convenient mechanical power. Ammonia offered excellent thermodynamic performance, but leaks demanded careful design, ventilation, and trained operators. By the late 19th century, refrigeration was expanding from experiments into large industrial installations. Carl von Linde developed efficient ammonia systems that helped make mechanical refrigeration commercially dependable. Factories could now manufacture standardized ice continuously instead of harvesting an uncertain seasonal resource. Natural ice remained competitive for years because established harvesting networks could deliver enormous volumes cheaply. Concerns about polluted natural ice strengthened demand for controlled manufacturing and cleaner water sources. Mechanical cold storage slowed spoilage and allowed merchants to hold food beyond local harvest cycles. Cooling extended storage time, giving producers and sellers greater control over when goods reached markets. Refrigerated rail cars connected distant farms and slaughterhouses with rapidly growing urban populations. Cold transport enlarged food markets, altered diets, and weakened the strict connection between season and location. Ocean-going refrigeration made it possible to move perishable cargo between continents rather than nearby cities. In 1879, the Strathlevin carried successfully refrigerated meat from Australia to Britain. Refrigerated shipping reorganized agriculture by linking remote grazing regions with dense industrial cities. Artificial cooling changed where food could be produced, stored, transported, and sold profitably. Cold chain preserves temperature continuously, from production through transport, storage, retail, and final use.
A brief warm interruption can accelerate spoilage, even when products are cooled again afterward.
Rapid cooling slowed bacterial growth and helped cities receive safer, more consistent dairy supplies. Pasteurization reduced pathogens, while refrigeration prevented surviving microbes from multiplying quickly afterward.
Large refrigerated displays helped supermarkets offer broad food selections under one roof throughout the year.
Domestic refrigerators removed daily ice deliveries by placing a mechanical cooling cycle inside the home. Many early household refrigerants worked well, but could poison occupants or ignite after a leak. Hermetic compressors reduced leakage by enclosing the electric motor and compression mechanism within one sealed housing. Expanding electric grids made automatic household refrigeration practical for a rapidly growing number of families. Reliable home cooling changed shopping habits, food storage, household labor, and expectations about freshness. Refrigeration delays deterioration rather than making food permanently safe or biologically inactive. Freezing slows change much more strongly by converting much of the food's water into solid ice. Large ice crystals damage texture, while rapid freezing generally creates smaller crystals and better quality. Quick freezing methods made frozen foods more appealing by preserving texture, flavor, and appearance. Frozen distribution created entirely new products and separated food availability from immediate harvest seasons.
Medical refrigeration protects temperature-sensitive vaccines, blood products, medicines, and biological samples. Health systems must preserve controlled temperatures through every transfer, including remote clinics and unreliable grids. Efficient solar refrigerators extend medical cold chains where conventional electricity is unavailable or unstable.
Air conditioning applies refrigeration to indoor air while also controlling humidity and circulation. In 1902, Willis Carrier designed a system to control humidity for a printing process.
Mechanical cooling allowed larger buildings to depend less on open windows, courtyards, and natural airflow.
Affordable air conditioning supported economic and population growth in regions once constrained by extreme heat. Cooling improves health and productivity, but it also creates substantial and growing electricity demand. Poorly designed cooling can worsen peak demand and add waste heat to already hot neighborhoods. Better insulation, compressors, and controls can deliver the same cooling with much less electrical energy. Reducing unwanted heat entry lowers compressor workload before any improvement to the refrigeration cycle itself. A simple failed gasket can waste energy by allowing warm, moist air to enter continuously. Clean coils and unobstructed airflow improve heat transfer and reduce the pressure burden on compressors. Variable speed compressors reduce cycling losses and maintain steadier temperatures under changing loads. Central systems can serve many refrigerated cases efficiently, but long pipe networks increase leak risks. Leaks waste refrigerant, reduce performance, and may release chemicals with serious environmental effects. Engineers sought refrigerants that were non-flammable, less toxic, stable, and compatible with compact appliances. Some stable refrigerants survived long enough to reach the stratosphere, where sunlight released reactive chlorine. Chlorine could destroy many ozone molecules through repeated reactions, rather than being consumed immediately. Measurements revealed severe seasonal ozone depletion over Antarctica, turning refrigerants into a global policy issue. The 1987 Montreal Protocol coordinated international action to phase out major ozone-depleting substances. Later refrigerants protected ozone more effectively, yet several still trapped heat strongly in the atmosphere. A cooling system affects climate through both its refrigerant and the energy required to operate it.
Engineers increasingly reconsider natural refrigerants, whose environmental impacts can be lower when systems are properly designed.
Carbon dioxide systems avoid major ozone damage, but require components designed for much higher operating pressures. Ammonia remains highly efficient for industrial refrigeration, where trained staff and strong safety controls are available. Hydrocarbon refrigerants work efficiently in small sealed appliances when charge limits and ignition controls are respected. A heat pump uses the same basic cycle as a refrigerator, but can move heat in either direction. Even cold outdoor air contains thermal energy that a heat pump can collect and concentrate indoors. Compression raises refrigerant temperature enough for it to deliver useful heat inside a building. Heat pumps can deliver more heating energy than the electricity consumed because they move existing heat. Modern refrigeration technology now supports both climate adaptation and efforts to reduce fossil fuel use. Reliable electricity is essential because refrigeration stops moving heat whenever compressors and controls lose power. Thermal storage shifts cooling production to quieter hours by storing energy in frozen water.
Flexible cooling systems can reduce costs and emissions by operating when electricity is cleaner or less constrained.
Modern controls improve efficiency by matching cooling output closely to real conditions instead of fixed.
Condition monitoring can identify developing faults before they waste energy or interrupt critical cooling.
Repairable equipment lasts longer and reduces the material cost of replacing entire appliances after small failures. Proper recovery prevents refrigerant release and allows valuable fluids or materials to be reused safely. Artificial cooling underpins enormous economic systems that most people notice only when they fail.
Access to reliable cooling increasingly affects nutrition, health, productivity, and survival during
Expanding cooling responsibly requires efficient equipment, dependable power, and designs suited to local conditions.
The cleanest cooling demand is the heat prevented from entering a building in the first place.
Correct sizing improves efficiency, comfort, and moisture control while reducing mechanical wear. Efficient cooling depends on the complete installation, not only the compressor or refrigerant chosen. Modern vapor compression refrigeration still revolves around 4 components linked by one repeating fluid cycle. The evaporator creates useful cooling by absorbing heat as refrigerant changes from liquid to vapor. The compressor supplies the work that drives refrigerant around the loop and elevates its temperature. The condenser transfers both absorbed heat and compressor energy into the surrounding environment. The expansion device restores low pressure so refrigerant can evaporate and absorb heat again. The refrigeration feels like manufactured cold, but physically it is organized heat transfer powered by machinery. Centuries of trade, science and engineering transformed seasonal ice into dependable cooling available anywhere. Manufactured cooling changed what humanity could eat, where cities could grow, and how medicine could travel. The next refrigeration revolution must expand access. While reducing energy use, leakage, and environmental, humans learned to manufacture winter by building machines that move heat exactly where we choose.
A simple cylinder of boiling water eventually reshaped factories, transport, cities, and the global economy. Before steam, most mechanical work depended on muscles, animals, wind, or flowing water.
Water wheels were effective, but rivers decided where factories could operate and how much power they received. Growing towns demanded more coal, forcing miners deeper into the ground that constantly filled with water. Flooded shafts closed valuable mines because existing pumps could not remove water quickly enough.
Horse-driven machinery consumed land, food, and labor, while delivering only modest power underground.
Heating water creates expanding vapor, turning stored fuel energy into pressure that can push objects.
Cooling steam reverses the process, shrinking its volume and leaving a partial vacuum behind.
The breakthrough required more than steam. Inventors needed valves, cylinders, pumps, and reliable timing. Steam power emerged through centuries of experiments rather than one sudden moment of invention. Nearly 2,000 years ago, Hero described a sphere spun by steam escaping through bent nozzles. Reaction from the escaping jets produced rotation, proving that heated water could create motion. Hero's device demonstrated a principle, yet it could not deliver useful industrial power efficiently. Ancient craftsmen lacked the materials, manufacturing systems, and economic pressure needed for a practical engine. 17th century experiments made atmospheric pressure and vacuum understandable enough to become engineering tools. Once a vacuum formed beneath a piston, ordinary air pressure could produce a powerful stroke. Denis Papin explored using steam and condensation to move a piston inside a cylinder. Papin's safety valve addressed a central danger by releasing pressure before the vessel failed. Promising experiments remained isolated because full-scale cylinders, seals, and control systems were still unreliable. Economic pressure from flooded mines finally turned steam research into a practical engineering race. Thomas Savery patented a steam-powered pumping system in 1698 for removing mine water.
Savery marketed the machine as the miner's friend, promising relief for waterlogged workings.
First, steam filled a sealed vessel and displaced the air already trapped inside.
Next, cooling condensed the steam and created a partial vacuum inside the vessel.
Atmospheric pressure then pushed mine water upward through the suction pipe into the chamber.
Fresh steam pressure forced the collected water upward through a second pipe toward the surface.
Savery's pump avoided a piston, making the concept mechanically simple but physically constrained. Vacuum could raise water only from shallow depths, far below what many mines required. Greater delivery height demanded higher pressure from boilers that contemporary metalworking could not always contain. Weak joints and uncertain pressure control made early steam pumping hazardous as well as inefficient. Repeated heating, cooling, and pressurizing consumed large amounts of coal for limited pumping work.
Savory's design found limited uses, yet it rarely solved the deepest mining problem it advertised.
Nevertheless, Savory proved that continuous steam cycles could convert heat into practical pumping. The next breakthrough replaced pressurized water vessels with a piston driven by atmospheric pressure.
That new arrangement became the atmospheric engine, the first widely practical steam-powered machine.
Thomas Newcomen and John Calley combined practical metalworking, plumbing, and earlier steam ideas.
Their machines separated the power cylinder above ground from pumps operating deep below.
In 1712, a new common engine began pumping near Dudley and demonstrated practical industrial power.
The towering structure converted a repeating steam cycle into long vertical strokes for mine pumps. Low-pressure steam filled the cylinder while the heavy pump rods lifted the piston upward.
The upward stroke prepared the cylinder for the engine's true power-producing event. Cold water injected into the cylinder condensed the steam almost instantly. Condensation left a vacuum below, creating a large pressure difference across the piston. Atmospheric pressure pushed the piston downward, which is why Newcomen's machine was called atmospheric. That working stroke raised pump rods and moved water toward the surface through staged pumps. After drainage and steam admission, gravity reset the beam for another power stroke.
Mechanical valve timing eventually allowed the engine to repeat its cycle without constant manual control.
A simple plug tree mechanism synchronized steam, injection, and drainage with the moving beam.
Using atmospheric pressure reduced boiler risk, but demanded heavy structures and large components.
Newcomen engines reopened drowned workings and made deeper coal extraction economically possible. Successful installations spread because mining districts urgently needed dependable pumping rather than perfect efficiency. Newcomen's appetite for fuel mattered less where low-cost coal sat beside the engine.
Every stroke reheated and recooled the same metal cylinder, wasting enormous quantities of steam. Most fuel energy disappeared because condensation occurred inside the working cylinder itself.
Decades later, a faulty model engine exposed that inefficiency to a young instrument maker.
James Watt encountered the Newcomen design while repairing a university demonstration model in Glasgow.
The model consumed surprising amounts of steam because its cylinder repeatedly lost heat. Careful measurements showed that cylinder cooling, not merely friction, caused the engine's waste. Watt asked whether condensation could happen somewhere else, while the power cylinder remained hot. His answer was a separate condenser, a cold chamber dedicated to collapsing exhaust steam. Separating the condenser allowed the working cylinder to remain hot throughout repeated strokes. Steam could now condense rapidly in another vessel without reheating the cylinder afterward. The colder separate chamber also produced a more effective vacuum for the next stroke. An air pump cleared condensed water and unwanted gases so the vacuum could continue. A surrounding steam jacket further reduced heat loss from the cylinder walls. Side by side, Watt's arrangement used the same basic piston idea with far less wasted heat. Watt patented his method for reducing steam and fuel consumption in 1769.
Matthew Boulton supplied the capital, workshops, and business organization needed to commercialize Watt's improvement.
Soho's manufacturing network turned experimental components into repeatable engines for paying customers. By 1776, successful commercial engines began demonstrating major reductions in coal consumption.
Their business model linked payments to measured fuel savings, making efficiency financially visible.
Lower fuel costs made steam power practical in industries far from cheap mine-mouth coal. Closing the cylinder allowed steam itself to act above the piston instead of open air. Watt's double-acting engine used steam to power both the upward and downward strokes.
Double action increased output and created motion better suited to continuous industrial machinery.
Factories needed rotating shafts, not merely the back and forth motion used by mine pumps. A competing patent complicated direct crank use, pushing Watt's team toward another solution. The Sun and Planet gear converted each beam stroke into continuous rotary motion. A massive flywheel stored momentum and reduced the pulsing character of reciprocating power. Rotary steam engines could now drive entire rooms of machinery from one central source.
Watt's parallel motion linkage kept the piston rod aligned while the beam traveled through an arc.
A centrifugal governor automatically reduced steam flow when engine speed rose too far. This mechanical feedback system regulated power long before electronic sensors or computers existed. Pressure diagrams helped engineers diagnose engines and compare performance using measured cycles instead of guesswork. Watt popularized horsepower as a practical way to communicate machine output to customers. Centralized power allowed manufacturers to coordinate many processes inside a single production system. Steam released factories from seasonal rivers and widened the geography of industrial production.
Textile mills used dependable rotary power to run larger numbers of machines for longer hours.
Steam increased iron production, while better iron enabled stronger boilers, cylinders, and machinery. Energy, materials, and manufacturing improved together, accelerating industrial change beyond any single invention.
Steam power encouraged production schedules governed by machines rather than weather and flowing water.
Greater output arrived alongside harsh workplaces, long shifts, and new forms of industrial inequality. Coal-fired steam concentrated pollution around industrial towns and altered urban health and landscapes.
Stationary Watt engines transformed factories, but transport required lighter machines with stronger pressure.
Watt distrusted high-pressure steam because weak boilers could fail with catastrophic force.
Improved materials and machining gradually allowed smaller boilers to contain greater pressure more reliably.
High-pressure engines used steam itself as the main driving force, increasing power relative to size. Cornish engineer Richard Structure pioneered practical high-pressure engines around the turn of the 19th century. Structure demonstrated that a compact steam engine could move itself, rather than remain inside a building. Rails reduced rolling resistance enough for steam power to haul far heavier loads. In 1804, Structure's locomotive completed the first railway journey hauled by steam. The demonstration proved feasibility, although tracks and engines still required major improvement before widespread adoption. Advances in track, wheels, and boilers transformed isolated experiments into reliable railway systems.
Steamships delivered scheduled movement against currents and weak winds, reshaping inland and ocean transport. Steam transport reduced travel times and linked markets, resources, and populations across greater distances.
Higher pressures increased mobility and efficiency, but they also made boiler failures more destructive.
Defective materials, bad joints, overheating, and poor maintenance all contributed to explosions.
Engineers responded with better gauges, relief valves, operating procedures, and formal inspections.
Public failures pushed governments and professional bodies toward enforceable boiler standards.
Steam engines forced scientists to formalize relationships among heat, energy, pressure, and mechanical work. Thermodynamics explained why no heat engine can convert every unit of fuel into useful motion. Later engineers expanded steam through multiple stages and refined timing to extract more work. Steam turbines eventually delivered smoother rotation at scales suited to electrical generation and large ships. Modern power plants often use advanced steam systems even when their heat sources differ completely. Steam technology evolved from mine pumps into a broad family of engines rather than disappearing.
No one person invented the complete steam engine. Each generation solved a different obstacle.
Practical steam power required reliable heat, controlled pressure, sealed motion, and useful mechanical transmission. At its core, the engine converts thermal energy into controlled movement through repeated pressure changes. That conversion expanded production and mobility, while also deepening dependence on fossil fuel and industrial systems. The steam engine emerged step by step until engineers learned to make heat move the world. For more than 2,000 years, people have searched for a city that may have existed only inside one man's story. Every surviving description of Atlantis begins with two dialogues written by the Greek philosopher Plato. Plato said the story reached Greece through Solon, who supposedly heard it from Egyptian priests. But no Egyptian document confirming Atlantis has ever been found, leaving the chain dependent on Plato's own account. Plato placed Atlantis 9,000 years before Solon, far earlier than any known complex city described in his story. His Atlantis was built in rings, circular canals, bridges, harbors, walls, and a monumental center. It was described as wealthy, technologically impressive, and powerful enough to dominate much of the known world. Plato placed Atlantis beyond the Pillars of Heracles, usually identified with the Strait of Gibraltar. That single phrase moved the search from the Mediterranean into the Atlantic, and eventually across the entire world. The investigation begins with a basic question. Was Plato preserving history, reshaping memory, or creating fiction? Before testing locations, the clues must be separated from the mythology built around them later. Plato's dimensions describe an enormous capital and an island larger than many proposed archaeological candidates. The island supposedly held abundant crops, forests, metals, elephants, and a complex network of artificial waterways. Those details imply a large, warm, fertile territory, not merely a small volcanic island. Plato paired the circular capital with a huge engineered plain divided by canals and military districts. Atlantis then attacked the peoples inside the Mediterranean. until an idealized ancient Athens resisted it. This conflict is central to Plato's moral structure: imperial excess against disciplined civic virtue. After moral decline and military defeat, earthquakes and floods destroy Atlantis in a single terrible day and night. Plato even said the vanished island left an impassable shoal of mud that blocked navigation. A real candidate must fit many clues at once, not simply resemble one attractive detail. Plato often used invented stories and idealized societies to explore politics, morality, and human failure. Atlantis fits that pattern. A powerful society becomes corrupt, attacks others, and is destroyed by its own excess. Its story functions perfectly, even if no island matching every detail ever existed. But fiction can still borrow from reality, especially in a region shaped by earthquakes, eruptions, and sudden coastal destruction. That possibility leads to the most famous historical candidate, Thera, now called Santorini. Santorini's circular geography, volcanic destruction, and connection to the Minoans make it visually compelling. Yet a volcanic caldera is not the same thing as a city engineered in concentric canals. The Minoan world was wealthy, maritime, artistic, and deeply connected across the eastern Mediterranean. At Akrotiri, volcanic ash preserved a sophisticated Bronze Age town with architecture, trade, and remarkable art. The site offers something Atlantis hunters crave: an advanced settlement abruptly buried by a natural catastrophe. Around the 2nd millennium BCE, Thera produced one of the most powerful eruptions of the ancient Mediterranean. Ash reached far beyond the island, disrupting landscapes, travel, agriculture, and regional life. Caldera collapse and displaced water may also have generated destructive tsunamis across parts of the Aegean. Coastal infrastructure and fleets could have suffered heavily, weakening trade and communication. But the Minoan civilization did not disappear in a single day. It continued for generations after Thera. Plato's stated date is thousands of years earlier than the Bronze Age world of Thera and the Minoans. The chronology is a major problem for identifying Santorini directly with Plato's Atlantis. Santorini is also far smaller than the territory Plato described, and it lies inside the Mediterranean rather than beyond Gibraltar. The theory works best only if Plato altered the date, location, scale, and political story. Thera may have contributed memories of catastrophe without being the literal Atlantis of Plato's text. If Plato's location is taken literally, the search must move beyond Gibraltar into the Atlantic. One group of theories places Atlantis near the Gulf of Cadiz, where earthquakes, tsunamis, and coastal change are real. Remote images have repeatedly produced shapes that look promising, until archaeology demands stronger evidence. Without inscriptions, datable architecture, and a matching settlement, geometry alone cannot identify Atlantis. Another popular theory points to the Richat structure in Mauritania because its rings resemble Plato's city. The resemblance is striking, but the structure is a natural eroded dome far inland and vastly larger than a city. Its circles formed through geology and erosion, not through walls and waterways built by an ancient civilization.
The Azores have also attracted theories because they rise above the mid-Atlantic ridge.
But volcanic islands on oceanic crust are not fragments of a vanished continent, comparable to Plato's enormous island. Modern plate tectonics makes a suddenly sunken Atlantic continent geologically implausible. Atlantis is unproven, but real cities and landscapes have disappeared beneath water. In 373 BCE, the Greek city of Helike was destroyed by earthquake and flooding. Helike demonstrates how a real city can vanish quickly through earthquake, subsidence, and water. Pavlopetri preserves an actual prehistoric town beneath the sea, complete with streets and structures. Many ancient coastal landscapes drowned gradually as global sea level rose after the last ice age. These drowned worlds are real, but they usually vanished over centuries or millennia, not a single night. A credible Atlantis discovery would need a complete archaeological context, not a mysterious shape or isolated artifact. Different disasters leave different evidence: erosion, sediment layers, broken structures, subsidence, and datable occupation. The ocean floor is full of patterns that can imitate walls, roads, pyramids, and harbor shapes. Underwater archaeology must distinguish intentional construction from geology, erosion, and modern material. Geology does not prove whether Plato invented Atlantis, but it rules out many literal interpretations. There is no geological space for a recently vanished continent-sized island between Europe, Africa, and the Americas. Modern bathymetry maps the Atlantic floor in enough detail to reject an enormous sunken landmass. Islands can sink gradually as crust cools, erodes, and subsides, but not as intact empires in a single night. Rapid submergence is possible locally, especially during earthquakes, landslides, or volcanic collapse. A volcanic island can lose enormous volume suddenly, creating memories of land destroyed by the sea. Plato may have combined several familiar kinds of catastrophe into one perfected story. That would explain why parts of Atlantis feel historically plausible, while the complete package remains impossible to locate. The story's political and moral precision may matter more than its geographic precision. If Atlantis was designed as philosophy, searching only the seafloor may miss the point of the story. Atlantis did not remain inside Plato's dialogues. Later centuries repeatedly rebuilt it for new purposes. As ancient texts returned to European readers, Atlantis became a geographic puzzle, rather than only a philosophical tale. In the 19th century, writers transformed Atlantis into a lost mother civilization behind Egypt, Mesoamerica, and other cultures. Archaeology does not support the idea that one vanished Atlantic empire created the world's ancient civilizations. Real ancient societies have deep local histories that do not require Atlantis to explain them. Modern esoteric traditions added crystals, advanced energy, psychic powers, and technologies Plato never mentioned. Film, television, novels, and games turned Atlantis into a flexible symbol of lost knowledge. Because the original location is uncertain, Atlantis can be placed almost anywhere imagination needs it. Removing later inventions makes the central problem clearer. Plato is still the only ancient source for the complete story. That does not automatically make Atlantis false, but it sets a very high standard for claiming it has been found. Every proposed Atlantis can now be tested against the same evidence rather than judged by visual resemblance. Santorini fits volcanic disaster and Bronze Age wealth, but fails major chronological and geographic clues. The Gulf of Cadiz fits the western location better, yet no accepted archaeological Atlantis has emerged. The Richat Structure looks extraordinary from above, but its geology and archaeology do not match Plato's city. The Azores satisfy the Atlantic imagination more than the geological and archaeological evidence. Most candidates become convincing only when one clue is emphasized and several others are rewritten or ignored. A strong historical identification should make the evidence converge, not require continuous exceptions. No inscription, city plan, datable archive, or archaeological layer has identified a place as Plato's Atlantis. The absence of proof is not proof that every inspiration was invented, but it limits what can honestly be claimed. The most defensible answer may be that Atlantis is philosophy built from recognizable historical fears, and disasters. The problem is not a shortage of possible locations. It is the ease with which almost any circular or submerged feature can be made to resemble the legend. Near the Bahamas, the Bimini Road has often been promoted as an Atlantean structure, despite strong geological explanations for its formation. Regular shapes can emerge naturally when rock fractures along joints and is later exposed by erosion. Yonaguni's terraces look architectural, but geologists can explain much of the structure through layered sandstone, fractures, and erosion. Archaeologists do not identify cities from shape alone. They look for construction methods, occupation layers, tools, pottery, and organized space. Remote sensing is excellent for finding targets, but shadows, resolution limits, and processing can create persuasive illusions. A genuine discovery must preserve relationships between structures, artifacts, sediments, and time. Dating matters because a spectacular ruin from the wrong century cannot be Plato's Atlantis. The location must also fit the travel routes, polydimensionary, political geography, and scale of the original account. An empire powerful enough to challenge the Mediterranean should leave evidence beyond a single later philosophical narrative. When a theory survives only by changing every failed clue, it stops being a testable identification. A useful theory must risk being wrong. Otherwise, every absence becomes hidden proof, and every contradiction becomes part of the mystery. Atlantis survives because it feels both impossible and familiar, a perfect city assembled from real human anxieties. It promises lost knowledge, warns against power, and turns natural disaster into moral judgment. The city vanishes beneath the sea and reappears inside the text that created it. For Plato, Atlantis may have been less a destination than an argument about what societies become. That warning remains understandable, because powerful societies still imagine themselves permanent. The search will continue, because every unexplored coastline and strange formation offers another possibility. But the more evidence-y this is compared, the harder it becomes to defend one literal lost super-civilization. What remains is still extraordinary, a fictional or reshaped city that became more famous than many real ancient places. Atlantis may never be found, because the complete Atlantis may never have existed outside Plato's narrative. Yet the legend preserves real truths about earthquakes, floods, collapsing powers, and the human fear of losing everything. The most important discovery may not be where Atlantis was, but why people keep needing it to be real. Atlantis remains suspended between memory, philosophy, disaster, and desire. That uncertainty is not a weakness of the legend. It is the reason the legend never stops moving. Atlantis may be history, borrowed memory, philosophical fiction, or some mixture we can no longer separate. What we can say with confidence is simpler. The story is real, the search is real, and the city remains unproven. Beyond the pillars, the map still offers room for imagination. But evidence must decide what becomes history. For now, Atlantis belongs where it began, inside Plato's dialogues, and inside the questions they still create.
The lost city remains lost, not beneath a confirmed sea, but somewhere between ancient catastrophe and the power of a perfect story.
Look at this skyline. Nothing seems to move, yet the ground beneath it may be dropping year after year. Nothing appears broken at street level because subsidence often spreads slowly across neighborhoods instead of opening one dramatic hole. Yet satellites reveal motion too small for human eyes by comparing the ground from one pass to another. The ocean is only half the story, because flooding depends on water height relative to the ground beside it. Sometimes the shoreline becomes more vulnerable even when the ocean changes little, simply because the land itself moves downward. That difference is called relative sea level, the combined result of ocean movement and vertical land motion. Engineers call this downward ground movement land subsidence, a process that can be natural, human-driven, or both. Unlike a sudden collapse, regional subsidence may lower many square kilometers without producing a single obvious center. Whole neighborhoods can descend together, carrying streets, pipes, railways, foundations, and flood defenses with them. The danger grows when sinking land combines with storms, high tides, river flooding, or rising seas. Begin beneath the pavement, where the ground is not solid rock, but a layered mixture of sand, silt, clay, and water. Groundwater occupies tiny spaces between sediment grains and fractures, supporting part of the weight carried underground. An aquifer behaves like a water-bearing geological layer, not an underground lake with a giant empty ceiling. Pumping lowers hydraulic pressure around a well, drawing groundwatering water inward from the surrounding sediments. Water pressure normally helps hold sediment grains apart. Remove it, and more of the overlying load shifts onto the skeleton of the soil. Remove enough water pressure, and the weight above squeezes fine-grained layers that were previously supported from within. Clay and silt are especially important because their platy grains can compact when groundwater levels fall. Their grains rotate and pack closer together, shrinking the underground space that once stored water. Once compressed beyond its previous stress, part of an aquifer system may never regain the lost storage space. Surface elevation then drops because the total thickness of the underground sediment package has become smaller. Picture a thick stack of damp paper being pressed thinner, rather than a city falling into a hollow chamber. In this layers persistence intuationmentations, layers react differently. Will continkle downs and vinuith commendanes fording distursing vitations. Large connected pores let water move through sandy layers more readily, making their pressure response relatively quick. Tiny pathways make water leave clay layers gradually, so compaction may lag behind the original groundwater decline. Delayed compression means land may keep settling even after officials reduce pumping or rainfall returns.
During drought, reduced rivers and reservoirs often push farms and cities toward heavier groundwater use.
Urban demand keeps growing through homes, factories, hospitals, cooling systems, construction, and public services. When withdrawals outrun natural recharge for long periods, pressure falls faster than the underground system can recover. The groundwater surface can descend beneath many wells, forcing pumps deeper and increasing the stress on compressible sediments. Each operating well creates a drawdown zone, shaped like a broad depression in groundwater pressure. Many nearby wells can overlap. This turns separate drawdown cones into a regional pressure basin. Overlapping pumping effects can lower an entire urban basin instead of damaging only the ground beside individual wells. Structures usually move with the ground beneath them, so a tower may remain upright while its absolute elevation quietly falls. Some districts descend faster because geology, pumping intensity, drainage history, and construction loads vary across the city. Uneven motion is often more damaging than uniform sinking because roads, pipes, and foundations must bend across the gradient. A few millimeters each year can accumulate across decades, especially where critical infrastructure was designed for a stable elevation. Surveyors compare permanent reference points over time to detect whether the land has moved vertically. Continuous GPS stations record precise position changes, revealing gradual uplift or subsidence at specific ground locations. Satellite radar can map movement across entire cities, covering far more ground than isolated survey points. Two radar observations taken at different times contain tiny phase differences caused by changes in the distance to the surface. Scientists convert that phase shift into a map of ground displacement along the satellite's viewing direction. Interferometric synthetic aperture radar, or INSAR, makes slow deformation visible as patterns across space and time. Colored patches represent movement toward or away from the sensor, not temperature, pollution, or political boundaries. Repeated radar scenes create time series that distinguish seasonal swelling from persistent long-term sinking.
Satellite measurements become stronger when researchers compare them with GPS, leveling, wells, and subsurface instruments.
An extensometer measures changes in aquifer thickness by anchoring deep below the compressible layers. Groundwater levels explain when pressure changed, helping scientists connect pumping cycles with later surface movement. Coastal tide gauges measure water relative to the land, so sinking ground can appear as faster local sea level rise. Local sea level change can differ from the global average because currents, gravitational effects, and vertical land motion alter the result. Useful flood maps must combine ocean projections, land motion, tides, storms, rivers, and drainage capacity. Once these measurements are combined, a city that looked stationary becomes a moving landscape with distinct deformation zones. Mexico City offers a powerful example because dense development sits above water-rich sediments deposited in an ancient lake basin. Long before modern streets,